Okay, so I just want to do a little introduction for Vittorio's talk. I wanted Vittorio to give this talk for quite some time, so I blame myself for not nagging him more in the spring to give this talk. But basically, Vittorio has published 5 papers in the prestigious European Journal of Astronomy and Astrophysics on stellar mixing. And I thought I would read the editor's foreword that was published the month before, preparing the community for Vittorio's papers, which I thought was quite nice and quite an honor, in fact. So the editor has said, mixing in stellar interiors plays a very important role in the evolution of stars. For instance, it carries fresh nuclear fuel into their core, thereby extending their lifespans. This mixing is caused by various instabilities, the most prominent being thermal convection, and generally these lead to a turbulent state. To model the transport of heat and matter achieved by such turbulence, generations of astrophysicists have used a prescription based on the mixing length, the mean free path of the turbulent eddies. The shortcomings of this crude prescription are well known, and Dr. Canuto has boldly undertaken to overcome them. Over the years, he has developed his Reynolds stress model, which he describes in paper 1. In the subsequent articles, he applies it to specific problems: double diffusion, turbulent transport of a passive scalar, transport of angular momentum, and convection overshoot. Now it is the turn of stellar models builders to implement this new formalism in their evolution code and to confront the results with the observations. Vittorio, please tell us all about it.
Thank you. Yeah, thank you, Mike. Yeah, it's true. Rebecca has been telling me that I was not doing my fair share of contribution to this gathering, and he was right. But then I look at this page. This is the front page of the issue, and the next one is what?
Right, the right button.
The right. Yeah, these are the paper that Michael was referring to. Here they are. Formalism, double diffusion, case of passive tracing, under momentum, and overshooting. And those were published in April of this year. But then I look at them, and and I found this is simply too technical for an audio like this. So I decided that I would try to do something slightly lighter, even though I'm going to use some of these results. So for those of you who are really interested in looking at this paper, here they are, in case you want to.
So on Earth, we're like 1, 2, 3.
Are we going to the question already, or? Well, that's fine with me.
Maybe you will get to it.
He will. He will talk about Earth. Just hold your hand.
I mean, but we need mixing parameterizations because we can't afford to resolve.
Are you stealing my talk or what?
How many orders of magnitude?
Well, why don't you stand up and give the talk?
He's a young whippersnapper.
He's a whatever this young. So anyway, here it is. This is sorry. This is in a way part of my career here at GISS. I started with stars, then I went to the Amberfield, I went to the ocean. So from the star, I just went all the way down. It's not a very brilliant kind of trajectory.
It's the wrong way.
It's the wrong. It's the wrong way, yeah. But since I've been here in a number of years, such that when I arrived here, most of you were not even born. No, not you.
Thank you.
At that time, we were doing basically astrophysics in this institute, and so much so, it was so famous this institute in those years. It's after World War II, by the way. That, for example, the Brits. Now, there are British people here. The Brits came down to this institute from England to announce the discovery of pulsars. Because they knew that it was a major discovery. They knew if they came to New York, the next morning it would have been on the front page of the New York Times, which it was. Because at that time, the New York Times had a science editor called F. Sullivan, who was a geophysicist by training, and he was just a wonderful science writer. So they came to the 3rd floor, and they announced the fact that that in Manchester, at the Jodrell Bank Radio Observatory, they had discovered what the Brits called the little green man at the beginning, but they didn't know. They always try to be funny, the Brits. So they called it little green. Actually, and then they realized that those were neutron stars and they were pulsars. And a couple of years later, they actually received the Nobel Prize. The woman who discovered that did not get the Nobel Prize. She was excluded by the Nobel Prize. Which
Jocelyn Bell.
Jocelyn Bell, which created a huge controversy. But she is such a nice person, she didn't mind. Anyway, at that time we were doing astrophysics big time in this place, and so we all started. And as the editor said, I don't know who the editor is, but he was right. For many, many years in astrophysics, you didn't need very sophisticated mixing. In astrophysics, actually, what they were doing, what many people still do in the ocean, it is convective adjustment. When you go in a situation which is very convective, the temperature is so uniform that in order to conserve the flux, the diffusivity must be very large. So they put the diffusivity up to infinity. And they didn't need any better. So that's why there was no point of doing anything more than what they had at this time for many years, because they didn't need it. Then, as I will explain later on, heliosysmology came by, and heliosysmology is a brand new branch of science, which was actually initiated here at GISS, where we were all postdoc in the good old times in which there were still 20 postdoc at this place. Now, heliosysmology has been something that has really revolutionized the astrophysics, because it's a way in which you can go inside the star. And that has demanded better model for, if I had sent the 5 papers 20 years ago, even though 20 years ago I would not have been able to write, but if I did, nobody would have accepted it, because said, well, why are you bothering with all these formulas if we don't need it? So, you know, you can only do science when people kind of need them, when the market, terrible to use the word market, but it's true, when the market needs something better, then you have a chance that the referee will say, yeah, comes in at the right place. So there are also something that you have to learn. Now, in answer to Matt Skelly's question, yeah, star, ocean, and atmosphere share some commonality. The star, usually, they're unstably stratified because the bottom of the star, the center of the star is very hot, and the top is not. The interior of the sun, for example, 50 million degrees. The surface of the sun is 6,000 degrees, which coincidentally is the same temperature as the interior of the Earth, which is a pure coincidence. But anyway, so the eddies or whatever, the warm gas at the bottom was to bubble up by Archimedes' laws, and that's what makes it unstable, which is the letter U. In the ocean, it's the other way around. The bottom of the ocean is cold, and it's colder than the surface, and that's where the temperature is gone up, and therefore it's stably stratified. Precisely because it's colder down here, it's denser, and so it doesn't move. There's no reason why it should start moving. And that's why it's so difficult to create turbulence in the ocean, whereas in stars it's natural. Unless you have the wind of the surface, which really moves the ocean by itself will stay perfectly happily stably stratified, which means there will be no great illumination. The atmosphere, of course, just in order to be democratic, it has both. It's both stable and unstable, depending where you have daytime, in which you have the Earth that is warm, and the surface of the Earth is warm, and so there is this plumes going up. And at night, which is the other way around. So you have in the atmosphere, you have both stable and unstable. The treatment of the tree is very different. It's much easier, in inverted commas, to study turbulence in an unstably stratified than in stably stratified. And I'll give you the reason in a second. Now, as Max was saying, the global code that we use, both in the atmosphere or in the ocean, or in stellar code. And here, our colleague Richard Stoddard, who tragically passed away 2 months ago, was one of the world authority in stellar evolution. He was my private confessor and private referee, and he read all those papers and made a lot of good observations. The stellar code, they do the same. They resolve the largest scale. And in answering a more quantitative answer to what Maxwell was saying, the ratio between the largest scale that you can resolve, which is more or less of the order of the size of the system, to the smaller scale of the system, which also goes under the name of molecules or stuff. It goes like the Reynolds number to the power 3/4. I will not derive it for you, but believe me, it goes to the power 3/4. So since this is one dimension, and since you have 3 dimensions, the number of degrees of freedom, as you would say in statistical mechanics, or the number of grid points that you have to use in numerical, it goes like the cube of that. So it goes like the cube of the Reynolds number to the power 3/4. 3 times 3 is 9, so it goes like the Reynolds number to the power 9/4. Now, if you go down on Broadway, if you look at the car, provided it's not driven by the Italian, otherwise the example doesn't work. But the Reynolds number driven with a car in Broadway is about 10 to the 5. So 10 to the 5 to the power 9/4 is a number that computer now can handle. So in principle, Renault, Mercedes, all these big companies don't need any fluid dynamics to do the subgrid, to do the Reynolds stresses in flux, because they can resolve a whole bunch of it. But the car in the street is what it is. If you go to the ocean, the Reynolds number can go up, and if you go to the star, the Reynolds number can be 10 to the 12. So 10 to the 12 to the power 9/4, don't even bother to do the multiplication, because it's a number so astronomically large that there is no computer in the world, thank God, that can resolve it. So there is a job for us to try to model all this huge amount of scales that are not resolved. So you put together your code, you resolve the largest scale, and then you come up with Reynolds stresses for the momentum equation, heat fluxes for the temperature equation, salt fluxes for the salt equation, for the salinity equation, or molecular weight, etc. So you have a huge job of having to parameterize, as the name goes, parameterize those scales that the computer will not able to resolve. Of course, we have to distinguish whether we're talking about horizontal and vertical. In the vertical scheme, you will have different now let's look at the ocean. In the ocean, let's go take the stable stratified, cold water at the bottom, so they stay there. Eddies are in general small because it takes energy to work against gravity. That's why eddies are small. Because you have to work against gravity that's stable stratified. So there is a number which was invented by Mr. Richardson in 1920 something. Richardson, who is a very interesting person. Mr. Richardson was a consensus objector, so he refused to go to World War I. And so when they told him that he had to go anyway, he said, "Okay, I'll drive the Red Cross car, so I will take the sick people to the hospital. I will never use a rifle or anything." And he did. So he did all. He is the grandfather of Olivia Newton-John, which is a very famous physicist too, on her own. So he was a very famous man because he discovered what is called the Richardson number. Now it's trivial, but at that time it was not trivial. It's simply the ratio between the Breuil-Weissaler frequency and the shear square. In other words, the denominator between two quantities. The Breuil-Weissaler frequency is the one that tells you that it doesn't want to have turbulence because it's stable stratification. The shear downstairs is the one that wants to have stratification. So you have the enemy and the friend on top of each other. Of course, since the Richardson number is very large, it means that the shear is very small, or vice versa. And so the Richardson number represents the boundary between the numerator that wants to maintain stability, and the denominator that want to shake the whole thing and make it turbulent. And so I'll tell you a lot about this Richardson number. Now, as far as the ocean, let's go to the mixed layer. The first 100 meters or so of the ocean is called the mixed layer because it's well mixed because of the wind, and the wind is the source, and the source brings in of the order 1 terawatts of energy. 1 terawatts, it's amount of energy basically that few terawatts is the amount of energy, electric energy being used by the world every year. Just to give you a figure. Now, if you want to have some typical numbers, let's have 200 is the diffusivity in the mixed layer. The molecular viscosity of water is 10 to the -3. The Reynolds number could be, in a way, defined as the turbulent diffusivity divided by the molecular diffusivity. In other words, it tells you how much larger is the turbulent diffusivity versus the one that is kinematic. This is a dynamical quantity because the turbulent diffusivity depends on the velocity of the field. The molecular diffusivity does not. The molecular diffusivity depends on the Lennard-Jones potential between the molecules. So there's nothing you can do. Whatever it is, it's a given number. Whereas the dynamical viscosity, in other words, the turbulent viscosity depends on the velocity of the flow, and therefore it's a dynamical quantity. Now, the fact that this is so much larger than this that the turbulent viscosity is so much less than this, it's also it's a blessing and a curse. It's a curse in the sense that you cannot use perturbation theory because it's a parameter that is 10,000 times larger than unity. So there's no smallness parameter in turbulent. That's a major problem. That all the perturbation theory that we learn in physics are useless. And the Reynolds number, if you look at the Navier-Stokes equation, is also the ratio between the term that would like to, the non-linear term and the linear term. That's why the linear term is represented by viscosity, and therefore it's between the non-linearity, which is the one that creates turbulence, and the molecular kinematic viscosity, which is this. Of course, that you can have Reynolds number more large than this. This is just one example. Now, due to stable stratification, as I was telling, which is what the ocean is, except some pathological cases which we'll discuss later on. Since the eddies are small, because large eddies cannot make it, you can use local model. Local model simply means that if you claim that this Reynolds stresses, or which is one, in other words, the correlation between two turbulent velocities, or the heat flux, the correlation between velocity and temperature, or the correlation between velocity and salinity, you can say, using some kind of analogy with the kinetic theory of gases, that this is proportional to the mean gradient of salinity, mean gradient of temperature, mean gradient of shear. And it's called local simply because the point Z at which you measure this is the same point at which you measure this. In other words, this equation should actually be read either way. It says that this is proportional, that this flux is proportional to the gradient times some diffusivity. Here, unfortunately, in oceanography we use K for the diffusivity, other people use D, but it says this is the diffusivity in centimeters squared per second for salinity, for heat, and for momentum, which are very much larger than the molecular value, larger of the order of that. But this is a local model. A local model simply means that you pretend or you assume that your turbulent quantity, 1, 2, 3, are given by the instability, the gradient at that same point. And this is true only if the edge is small, because if the edge is very large, and then you cannot pretend that the local description. I will give you an example of non-locality. Due to the fact that we have stable stratification, which is not true in the sun, for example, a local model in the ocean works more or less reasonably well. Now, you can see here they have you always have gradient, because it's only the gradient of the different quantity that create mixing. Because if you only have a very strong wind, but it's uniform, you create absolutely nothing, because with Galilei transformation, you go into a Commute system, you go with the flow, and the whole thing is gone. So it's only, but you cannot do a Galilei transformation on a gradient. So only when you have gradient, you have possibility of instability. So a gradient is always the quantity that comes in. Now you may have here the temperature maybe minus the you may do all sorts of refinement, but basically the concept here is that the gradient are the ones that are running the show. Without the gradient, you would not have. Let me see my notes here. Yeah. So okay. So what is there a critical Richardson number? In other words, is there a point at which stability wins? This is the thing, wins over the source of instability. Well, this has been going on for many years. Is there a critical Richardson number? Until recently, the models that were used to compute the Reynolds stress and heat flux, they were invented by these two gentlemen in Princeton in the early 80s. That is an absolutely heroic work. I mean, it was fantastic what they did. But they came up with a critical Richardson number of 0.2, meaning that if this is greater than this, in other words, if this is larger than 0.2, then the stability wins, and there's no way that you can have any mix. Now, empirical studies showed at the same time that that's not true, that it is 5 times larger. And in this group in 2002, 2001, we actually find out that was true, that the Miller and Yamada model of the early 80s needed some improvement, which I think we did, and when we did it, we got the order of 1. Now, again, I want to show you some data, because it's always useful. Here's the moment, the heat flux. Here's the momentum flux. In other words, this is the quantity W theta, this is what the UW. And you can see it plotted against the Richardson number. This one decays. Of course it decays, because the stronger is the Richardson number, the more stability takes hold of the situation. And here it goes, it really dies off at about 10, not at 0.2 as Mary Yamada said. There's a lot of still additional mixing that was not taken into account by the model, but that's science, you make progress as time goes on. So, but still dies. The momentum, even though the data are pretty scattered, but the momentum really doesn't, pretty stubborn, it doesn't die. Why does this die, why doesn't it? Because if we can go back once, this one is the one that, this one is the one that doesn't die, this one is the one that dies. Because the stability, the Brunel-Masala frequency is basically the gradient of the temperature. So between this guy and this guy, the one that feels more the stability is temperature. Because after all, this is the derivative of temperature. It's logical, or at least it's consistent, it's comprehensible perhaps, that the momentum should suffer less the effect of stability than the heat loss. And that's why this one has no chance, but it has to die sooner or later, not at 0.2, larger, this one keep on persisting. Another representative thing is to make the ratio between the heat conductivity, the turbulent heat diffusivity, momentum diffusivity over heat diffusivity. Since the heat diffusivity heated the most and it becomes smaller faster, this one grows. And that's why all these data show that the ratio, the momentum grows, the momentum decreases, the heat decreases, but the heat decreases much faster because it's heat. And our model, of course, is this line in the middle, otherwise we would not have shown it to you.
So what were they missing?
Well, that's a good question. They were missing nothing that they could, we have to be very fair, nothing that they could do at that time. The knowledge in the closure business was not such that they could do anything better. So in 1980, they really did the very best they could, and this 0.2 is not their fault. I mean, in 2001, we had so much more knowledge and literature in the closing of turbulence equation. That, by the way, it was caused by a pressure correlation, which intuitively we did not expect it would have this effect. I have to tell you how much we understand what you do. But we using, honestly, by using the best closure we had, and this is the work that Heat Chang has been doing, that's what it was missing, a better closure of the pressure correlation. So, that's it. Oh, let me talk about double diffusion, because double diffusion is something that happens both in the ocean and the star. So, in the star, I use the Mediterranean Sea as an example. You have warm water and salty water under cold water at the bottom and fresh water. Water in the Mediterranean is very salty because there's a lot of evaporation. That's why seafood is so good in the Mediterranean. As a European, I must eat seafood. Okay? So, cold and warm. So what does it mean? It means that the temperature part is stable, because this is cold, it doesn't want to move. The salt is the one that's creating instability, because salty water are denser water. So this one tries to fall down. So that's why it's called salt fingers. So here we have all these very nice fingers coming down. This one doesn't like it, they want to stabilize the system. This one wants to destabilize it, and so you have salt fingers. In the Mediterranean, this is what happens. Then you have diffusive convection. This is just the other way around. Warm and cold become upside down. Now cold is on top, warm is on the bottom, fresh is on the top, salt is on the bottom. So this one now is stable, yes, because salty water is dense. This water has no desire, no need to move. This one is warm and it wants to move. So this one tries to move and create turbulence, create mixing, but this one opposes it. So there is a fight between the two. Much in the same way as there was this Richardson number, which was the relation between the temperature that wants to stabilize and the sheet that wants to destabilize. Here you have to introduce another number, which is called the density ratio, between the gradient of salt and the gradient of temperature. So this is and salt finger in laboratory occurs when this R rho is less than 1. Okay, and diffusive convection when R rho is greater than 1. And there is a huge set of experiments which I'm going to show you. Okay, this is maps of where salt finger and diffusive convection may occur in the ocean. So for example, salt fingers occur here, they occur here. I lost the Mediterranean Mediterranean.
Yeah, where's the Mediterranean?
Yeah, I know.
You made such a fuss about it.
There's been so much fuss about it. I have to give this map back to whoever gave it to me.
Nice map.
Nice map, yeah. Yeah, the salt figure
It
Mediterranean.
looks like you have a boat.
Yeah, oh yeah, sure. Because in Mediterranean there are so many currents. So this is important. For example, if you go down to if you go down to the ACC, this doesn't mean that was measured. Let's be clear. This means that these regions are such they're prone. I mean, they're prime to DC, of course. Now remember that these salt figures and double diffusion can only exist if you have very weak turbulence. Because if you have imagine you have a lot of bunch of salt figures coming down like this. If you have strong shear, it just wipe them out completely. So in the mixed layer, there is no chance that you have salt figures. Even if they try to be there, the shear is too strong. So you have to wait to go below the mixed layer in order to have some sign of double diffusion. And this is an experiment. It's called NATRE. NATRE means North Atlantic Tracer Release Experiment. This is an experiment. It's from Woods Hole and Cambridge, UK. They went to NATRE, which is located near the where in the middle of the Atlantic. Not for the Canary Island, yeah. And they threw in at 400 meters, or way below the mid layer. They put in SF6, which is a gas that doesn't destroy the local phase. And they follow it for 2 years, and they measure finally a measurement, which is good. And they measure in effect that salt diffusivity is 1.38 in diffusivity. So well, there's no big number, yeah, but you know, it shows that the effect is really there. So I was telling you, salt figure is salt and warm over cold and fried, the Mediterranean Sea. Now, what is the stellar analogy? There is a stellar analogy, which, by the way, our colleague Dick Stubb, that's the one I was telling you before, was one of the first ones to point out. Helium flash. Now, you know that stars, as she was ready before, stars are essentially places where you cook. You cook all the elements from helium, from hydrogen to helium, etc., etc. But there are usually it's spherically symmetric, so they're being cooked and they expand. But there are cases in which this helium burning, which is the one that gives rise then to carbon, a boron, etc. The helium flash does not occur in the center, but occur off center. Somewhere on the star, there's a place where this burns. Boom. If it does, then in that case, at that point you have a higher mean molecular weight because you have helium being created, whereas the center. So it's like if you're having more salt, in a way. It's like having salt in water. You have hot. It's hot because that's when you have the nuclear reaction. And down in the mix, it's cold. I mean, colder means it's not as warm as it is. And the low mu gas. So this is exactly the analog of salt figures. And Dick Stubb is the first one that many years ago came up with the idea of saying that this helium flash, off-center helium flash, should be treated differently because it gives rise to a completely different mix.
What's the order of magnitude?
Oh, it is, of course, yes. So salt figures, even though the astrophysical community has its own nomenclature, but they adopted salt figure, even there's no salt and stuff, they adopted, but because there's no other terminology, it's so clear, the salt figure is so nice, that they use this terminology. Now, diffusive convection is not very nice, because I don't like, but that's true. Anyway, this is exactly the opposite. It's called, as I was telling you. The Red Sea, for example, has cold and fresh water over warm and salty water. In other words, the warm water at the bottom is the one that tries to bubble up because it's unstable, but the salty water at the bottom is trying to damp this. The star analogy of semi-convection is a supernova. A supernova is what happened at the end of life of star when they explode, and there was one in 1987 that was quite the case because you may remember. It was a very serendipitous event of this supernova in 1987. There was
the closest one ever observed.
The closest one ever observed.
Cloud.
That's right. And
No, the closest in modern times. And
Modern
crap
times.
everywhere was
Modern
like
times.
8,000 miles.
he teaches astronomy, so
Can't build that.
you know, cannot. With Armando, there's no chance. No, even when you're right, he's subjective. Imagine when you're wrong. I live with him for many years. But in defense of what you say, this was a case that was really fantastic because they observed it in the Southern Observatory in Chile,
Las Campanas.
and they said immediately that there was no internet at the time. Was there?
Telefax.
Telefax. The old observatory, they were banned. They went and looked at this at the supernova 1987, and the dispute in stellar community was whether it would happen to the red or the blue edge of the red giant, and the treatment of convection was a very important one, and they treated it in a very poor way because at that time they couldn't do any better. But at least they realized, those who were smart enough to know this kind of business, then the difference between red and blue, whether there was a red or a blue edge, it was actually due to the fact that it was semi-convection. So that was an interesting, Now, there is a lot of laboratory data about salt figures, and the reason why I show you this is only because I want to show you that the laboratory data, all these people that have been doing it for years. Here they plot is essentially the ratio between the heat flux to the salt flux. So this, it goes down with this density parameter. But the real message I want to give you is that here this is our computation. For a Richardson number of 5, Richardson number of 5 means that shear is still rather strong. Because remember, shear is downstairs. When you go to a Richardson number of 10 to the 4, it means that the shear downstairs is very small. Basically, there's no shear. And so they simply show that if you have still some shear left over, 5 is a characteristic number, this curve has nothing to do with the data. Whereas if you go to 10 to the 4, it could be 10 to the 5. I think the check you told me that it's saturated. When you really kill the shear, then you can have theoretically a curve that is more or less along this. So it's really, because in laboratory when they do double diffusion, they don't put any shear. Because, and that's bad in a way because we would like to have some data with shear because I think that, so the data that we have on which we can test our model, these lab data, are always for infinite Richardson. They were before our model were right. Now we have our laboratory data from DC for diffusion convection only. Also, they also have this bunch of data, and also you can see that you have Richardson number that could be typical of the mixed layer, for example, 0.1 or 1. This curve, this theoretical curve, the model produces curve. They have nothing to do with the data. But if you go to a very large Richardson number, meaning that shear has gone by the wayside, then you can start having some reasonable fit. I don't know which to fit. Some reasonable fit to data. So those are phenomena that suffers a great deal of the presence of the Richardson. Now, in natural experiment, they also all this measurement, they also come up with something very interesting, which we consider to be a great challenge. Rather than writing the diffusivity, say you write it in a way that it's a three parameter, it's a dimensional parameter. It's called the efficiency of the mixing efficiency. Mixing efficiency means the following: when you have an unstable situation like in the sun, kinetic energy goes into potential energy. Whereas when you have an unstable situation, it's the other way around. It's potential energy, which we call a Baroclean instability. It's got a lot of energy and it gives it to the kinetic energy. So this gamma represents the efficiency which means potential energy creates kinetic energy. Usually people took for many years in the literature, in the oceanic literature, they took 0.2, 20% of the energy. Now this new experiment shows that it depends on the Richardson number. When the Richardson number is less than this, or the Richardson number is 5, you can go from here to here directly. This efficiency, here at this point, salt fingers have no chance of showing their good. Simply because there's too much shear. As I was telling you before, they're being wiped out. When the Richardson number becomes very large and shear decreases, salt fingers have finally a chance to show up, and this can go up to 60%. So our curve, which is this, with solid curve, which Armando and he did, our model, this was a very tough test because we didn't know what they would reproduce. I don't think of any other model that reproduces this. I only say that this is probably in geophysical research center. So this means that our model was, because I was telling you before, all the data before this, which was laboratory data, they had no shear whatsoever, no Richardson number, or infinite Richardson. Finally, this, which is the real ocean, because this is natural, and then also this other measurement, this is the real ocean, where there is always some shear, you cannot just preclude, and show that the shear has an effect, and it allows the efficiency to get larger, because finally salt finger have a chance to show what they can, what they're good at. These are the measurements that finally were made of heat diffusivity, is already centimeters squared per second. Of course, the molecular value would be here, in depth versus depth. Heat, salt, mass, and concentration. Very few measurements, you know, but thank God, I mean, one is not a large number, but compared to 0, believe me, it's a large number. And so our model was checked against those and they reproduced it. Now, let me go to deep convection because this is the closest similarity between stars. Deep convection in the ocean occurs in practically 3 places, let me memorize. One is the Labrador Sea, one is the Gulf of Lyon, and one is the Weddell Sea. Now, in the let's say just one example, but the physics is the same. The strong wind coming from Canada, well, this is an oxymoron. Strong wind always comes from Canada. Low wind, very strong. At that latitude, they lower the temperature in the Labrador. So there is a huge loss of buoyancy. Okay? This cooling from above, so water gets very cold, then becomes very dense from the temperature side. They evaporate, and therefore, so of course you don't evaporate salt. Salt remains behind, and so they're very salty, they're very cold, and the whole thing falls down. That's a perfect recipe for convection, because the whole thing is very dense at the bottom, at the top, and it falls down. Now, this process is very fast. They last for days, and they have to cover 1 or 2 kilometers. So the velocity of these plumes, if you want, is a few centimeters per second, which also means that experimental observation is a big problem, because unless you happen to be exactly there, you know, you can, it's a big, huge sea. If you're not there when it happened, and there were people in the Gulf of Lyon that were just very lucky by their own record, and we just happened to be in a place where the Mistral, not the train, the wind, came by and gave us this huge convection, which happened to be there, so we made a measurement. So the Labrador Sea is one example of which we have this. Now, as you said, this is cooling from above. The sun, in a way, is warming from the bottom. So those are very different physics. In the atmospheric analysis, is cloud cap, planetary boundary layer. So the analogy between, because you can have it both warming from the bottom or cooling from the top. And in stellar analogy, there is also something that I'm going to tell you later, cooling from the top also, which is due to change in capacity. Now, let's look at small eddies and large eddies. Of course, eddies are not spherical, but you know, simplify leaves this life. I mean. So suppose you have an eddy in an environment like in this room of the depth or height, h. If you have only small eddies, as I was telling you at the beginning, small eddies can be described by a local phenomenon, namely that the gradient, the temperature gradient at z gives you the flux at z. Well, in this problem, since it's so local here, this guy doesn't know the extent is h. So there is no h. Why should there be any h? Because this guy simply doesn't know. However, when the eddies become large, then you can it must be large means it could be of the order of h. At this point, if you have large eddies, then this local model simply don't work anymore. You have to use no local model. Now, of course, no local model can be written in any thousands of ways. But one way of saying, for example, saying that at the point z, it's not true that this is given by this, that this formula says it's given by the integral from the bottom all the way to the top. So you integrate all the fluxes. Of course, this has a tilde here, which this didn't show up. Which means that you're simply adding up all the turbulence, all the contribution of all the edges one up there until the point. So here h will appear. That's what this non-local model different from the non-local model find here h. Size of the so this this you can say this is very this is a diffusion formula. See? Right here. It's typical diffusion. This is no longer a diffusion. I mean it's a complicated diffusion. I mean still, but it's an integral, so there's a kernel here, and so I would say that this is much less diffusive than now. Next thing that will please some people here. This is a measurement in Labrador of deep convection. This is 2002, February 2002. This box here, which goes under the name of Lavender box because she's the one who published this paper. These are the places where the deepest in which blue means 400, 600. In other words, this plume fell down 400, 600 meters. Red is 800 meters. And all the other places are the order of 200. So this is the region of deepest convection in the Labrador Sea. This is and all these places here. So these were the data that we were trying to. Well, that's the only data we have 2002, and we're still trying to. Well, this is what we did in 2004. This is our model. For the lavender data, we get 1 kilometers here, 1.2. At least we have 3 points more or less in the box, which is not so bad. But we also predict places and which we did convention of 1.2 kilometers, which are not observed. So this is a real challenge. And nowadays we're doing even worse. Oh, this is the gift from each end. These are data from Mrs. Dong, who is down in Miami. And this is the ACC. This is immediately adapted to the ACC. This is, if I could only read this, what does it say here? January, February, March, and you go. So if you go in their winter, which starts, what is this, July, August, September, you see the immediately adapted reaches values of 400 meters. Okay, easily. Whereas if you go in January or February, which is their summer, of course, the mislay is not that deep. It's 100 meters or so. So these are the observations. That's what we have observation. So how well do we do in our model with this? Well, KPP model, which is a mixing model in the vertical, which is very commonly used, gives result of which, of course, have more or less the same feature. But if you look more in detail, it gives, first of all, much more extended region of 400 meters that are not observed. So the region is much broader than what is observed. And there are spots here, very dark blue. This choice of color is really, really terrible. But we have to follow the data. So it's too deep in some places, and it's too extended in general. Our model is this, which is a little bit better because you see the red region, which are 400 meters as the data, are limited to certain bands. I would say this is here, for example, the previous model, this is all red. Now this is no longer red. So they do a slightly better job, or even more than slightly. We do a slightly better job. Now, inside pyramid. So let's talk about the sun for a second. Oh, you succeeded this time. The radius of the sun is more or less 10 to the 10 centimeters. The sun, as I was telling you, has a temperature of 15 million degrees here, 6,000 degrees here. So the energy is being produced in the core, is being propagated. It's being propagated by photons. Photons, as you know, are terrible guys because they chit-chat with everybody. Every electron they find, they have a huge cross-section, the quantum cross-section. So they're not very reliable as far as transport. You know, they're very lazy, they talk to everybody.
Tell them how long it takes them to get out.
That's all it takes to go out.
Tell them how long it takes.
You know that. Tell them it is. Oh, that's a good question. How long does it take for a photon to walk
Get out of the center to the top.
to the top?
Come on, Professor.
Huh?
Half a million.
Half a million. That's right. So if you want it a bit faster, it will be 500,000. So, on the other hand, how do you move photons? Photons have, in electrodynamics, there's nothing you can do because it's a theory that you cannot change the charge of the electron, you cannot change the range of the electron, there's nothing you can do. So either you take it or not. So at one point, the star really, to put it very much, get sick and tired of this. And when you get to the last 30%, this is well, you guys are not doing your job. So it becomes competitive, very strongly competitive. 30% to the more, 30%, the last 30% in order, because it's running out of space, so you have to transport all this heat at the surface. The last 30% is convection. Now, as I was telling you before at the beginning, until about 20 years ago or so, this convection was treated exactly as it was treated in oceanography. They said, well, it's so these edges are so huge, you know, and the temperature, this convective is so strong that the temperature becomes basically constant. The temperature gradient is 0, the flux has to go there, so the diffusivity is practically extremely large. You can put any number you want. Oceanography did exactly the same. So that's why people for many years did not need any better than the mixing length theory, which is what this editor says. Any improvement was welcome, but was not needed, and nobody would use it. Then heliosismology came about, and as I was telling you, Douglas Gough, who is the man from Cambridge who was here postdoc in 1968-70, is the one who was actually at the forefront of this heliosismology. They invented this heliosismology, which is the same thing that they do in geophysics, in normal seismology. How do you know the temperature inside the earth? You do with that, just take a thermometer, you simply look at what happened to the P waves and the G waves that propagate. Well, it so happened the stars also tremble. They also have over and above rotation, they also have vibration. And through this heliosismology, which is the equivalent of our seismology, they could really pierce through this region, and they can give you temperature profile, or the velocity of sound to be precise. Velocity of sound out of which you get the temperature profile. Even in regions in which 30% of 10 to the 10 it's a lot of kilometers. Nobody can go there. There's only student going there, but heliosismology can. And they discovered, lo and behold, that this convective zone has a region down here which they call overshooting, and which is this completely misplaced. The sizes are not. This is much smaller than this one, but which is the major topic. That's what one of my papers was, because nobody knows exactly how deep is this zone. Why is that? Because these plumes that are coming down here are coming. As soon as they get to the point at which convection, in principle, is over, it's like the acceleration is zero. But acceleration zero doesn't mean velocity zero. So this plume keep on going, even though they have no more force. The force is gone, the acceleration is gone, but they have a residual velocity. So they keep on penetrating into this stably stratified. This is stably stratified regime. So you have plumes going into a regime in which which is stably stratified because there's no source of energy. Okay? And so the quantification of the overshooting has been one of the major, it still is one of the major problems. So now people, of course, have extended heliosismology to stars, to many more stars, and this is the future. So 30% is governed by convection, either from below, cooled from above, and blah, blah, blah. Okay, overshooting. There's an unsolved problem. So what is the extent of the overshoot? In unit of pressure scale height, which is one way of measuring. Is one pressure scale height 0.2, 0.3 later? Well, one equation just to, if you take the equation for the kinetic energy, and this is the flux, and I was telling you before, this is the source. On the right hand side, there's always the source of the same. This is dissipation, this is the convective flux. And the convective model we used thus far, they take 0, 0, everything is 0, so production is equal to dissipation, and that does it. In the overshoot, you cannot do that anymore. Why? Because the right hand side is negative, because the flux down is negative. The heat flux is negative, exactly as it is at the top of the atmosphere. If you look at the flux from the surface of the Earth all the way up, you keep on decreasing, and then when you get to a certain height, the flux becomes negative. So it's exactly the same as it happened there. So if this is negative, this of course is negative, then you cannot put negative plus negative equals 0. So that means that the left-hand side cannot be 0. So even if you go stationary, that means that you have to have this. And this is a non-locality. This is the flux of kinetic energy. Kinetic energy is already a square of a velocity. If you put the flux, then it becomes a 3 velocity, so it's a third order moment. It says here, the right-hand side is negative, but this is negative, this is negative, the left-hand side has to be negative. So you need a non-local theory. You need a flux of turbulence, which is a non-local source. That's why you need non-locality, because you're going into the place which... So Tom stance is not the name of the restaurant downstairs. This is a third order moment. And then I was telling you, the flux is a third order moment. Now if you go into turbulence, which I will not bother you, but the third order moment can be derived from the fourth order moment, because that's the chain of turbulence. Every moment that you can have always implies a higher. That is the closure problem. That if you write the equation for a certain moment, you have more unknown than equation. So at one point you have to clip them, you have to cut them, otherwise you don't solve the equation. Now, tau can be derived from foam, fourth order, and so on. Fortunately, as of late, there were some measurement. People they measured the atmosphere in some fourth order moment. So what we did, he changed it because he's the one who does the work. Well, he wrote this equation. I'm not even bother to. It's just too complicated. Anyway, we brought this fourth order moment, C4, all these fourth order moments in terms of third order moment. And there were this data, these are the aircraft data. What are the aircraft? Circle are the aircraft data. Nicely scattered, of course, because it's a different fourth order moment. This is the fourth order of the velocity squared times the temperature, velocity squared times temperature. There's a lot of fourth order. And these people here, fortunately, Harman and company, and in Hamburg, they measured this in a campaign in the north of Europe, and in the atmosphere, they measured the fourth order moment. Having this fourth order moment, we were then able to construct our third order moment, and the solid line, it's our model. Our competitor, Ryan Harman, have this dash line, which is as good as ours, I would say. So now we have a model for the third order moment. Now, because fortunately, rather than cutting it theoretically, which would have been very arbitrary, we have this fourth order moment. So now we have this one that I was looking at. This is the flux of kinetic energy. So we have a model now. If we want to, we can put it in. This is the one that we need in the ocean, for example. The third order moment, now we have it. And I only want to show you this one because I don't want to bother you with the other. But the point is that now, fortunately, we have a model. Whether this can be used, sorry?
Where the observation?
This is the observation that are the circular here. For this, I don't have it. Or at least, do we have observation for the third order moment? Or no, we have them for a U square or no.
We began, yeah.
Yeah. Okay, here are the. Oh, this is W cube, which is part of this. You see, because Q square, this is U square V, W square V, and W cube. Because this is the kinetic energy. This is part of the observation. So we have a model. Whether we can use it in an ocean, that's a different story. Because this requires, these formulas are not simple. It takes a lot of time. So perhaps having this formula doesn't necessarily mean that you can use them. But in principle, we did our duty. Now, finally, the last two slides. Let me show you something a little bit general validity. When you write, especially with young people here, when you write an equation for any scale that you want, salt, temperature, concentration, mean molecular weight, you name it, you will have a time derivative, you have a mean flow, times the grade. On the left-hand side, you put all the diffusion process that you want. So Dij, this is model independent. Dij is some diffusivity, some tensor. I don't need to, for this argument, I don't need to specify what it is because I only want to discuss the difference in mixing and stirring. So let's take this tensor. A tensor I can always add, this is the tensor. I can always add 1/2 and subtract 1/2. Then I put the sum, big deal, right? So I put the one which is symmetric, I in j plus dji is symmetric because if I exchange them, it remains the same. And the one that I subtracted, of course, I got the index ij and ji. So if I change the index here, this changes sign. So this is antisymmetric. And successfully, I succeeded in writing A instead of F.
You wrote
S instead of A. This is antisymmetric. You could correct it, no?
Sorry.
Technically, it wouldn't
You
possible.
didn't have to.
I did that time.
I don't have time to correct all of your slides, Vittorio.
Okay. So this is antisymmetric. I apologize. This is antisymmetric. So let's put them in here. Let's put them in here. The symmetric part, I will not bother because the symmetric part is what gives you the standard mixing. That's what you understood for the mix. So let's look at the antisymmetric part, which is this character here. Okay? The antisymmetric part, now you take the derivative of two quantities, the derivative of the first times this, and the derivative of the other. Big deal. Now this one is 0. Why? Because this tensor here is symmetric. I and j is symmetric. This tensor here is antisymmetric, and the product of an antisymmetric tensor is 0, no matter what. So this is gone. Now this one here remains, and I'm going to call this, since the diffusivity always has the dimension of a centimeter squared per second, the derivative. So I'm going to call this a velocity, u star I, of course, because I'm summing over j. Why do I call it? Well, this, if I call this the derivative of the antisymmetric part of the diffusion, I call it the velocity, then this term here, I bring it on the left-hand side, and I have this velocity. The symmetric part has remained here. So what does this show? This shows that given any arbitrary diffusivity, it's not true that it only gives you mixing through in the sense of that we understand. It can also give you advection. This is an advection, this is not an advection. So, and this is model independent. So this is what is called stirring, and this is what is called mixing. And they're very different things. So much so that these two famous fluid dynamicists, when he was young and I was asking for a martini, he always asked shake and not stir, so he knew the difference. This idiot doesn't, because when they ask him, would you like it stir or shake it, he says, I don't care. That's what he says. So zero in fluid dynamics with this guy, and shaking and stir. So, you know, he is called stirring and shaking is back to the missing, but you. But when you go, since you're eating pizza, when you see a pizza guy doing the dough, kneading the dough, let me go back. What does he do? Which one of these two it does? Of course he uses this one, because he pulls the pizza. He says, you start. He pulls the dough, I'm sorry. He pulls the dough in and he pulls it out. He wants to mix it. But he's certainly not going to use the symmetric part. Any pizza store knows they cannot use the symmetric part. They use the anti-symmetric part. So they have this stir. They use advecting. In other words, they do mixing to advection. And so this is a so to think that, of course, if you have a one-dimensional problem, then you only have one. You only have this. You don't have this. But this goes to show that limiting the word mixing and stirring. I mean, when you put a spoon in a cup of tea, a cup of coffee, do you stir it? You do mixing. I think you do this. So, you know, you are advecting the flow. You don't stir. Stirring would be, mixing would be that you put a little vertical mixing. You do this. You don't do that, you know, because that's very close to molecular. It will take you forever. Because if you really want to do that, so you can put sugar in a cup of coffee and then wait until molecular mixing does it. And it will do it. It will take 3 weeks, whatever it takes. But it will do it. Okay? It's true. It's true. So you don't need any mixing. You can have sugar mixed in coffee by molecular mixing. It takes 2 weeks. If you do it with the little needle, just do it in the center, it will take a little bit less. So until you do it like this, and you do actually the stir. So you know, stirring and mixing are two different things. These people use shaking, which is the closest thing to mixing, and it turns out that in the ocean, just to conclude on some more, this in astrophysics they still have not digested this concept. But in the ocean, in the mixing property that we are studying, this is the most important one. This has been a major understanding in ocean, because for many years the horizontal stirring or mixing was always understood to be a diffusivity. So they keep on increasing the horizontal diffusivity by a factor of 10 or 100, etc., and they never got anywhere. Until they realized that it was not, and that's why I see some computation where they say, let's play with the diffusivity. They'll never work, because it's diffusivity. This is an advective process, nothing to do with this. When it was realized in 1990 or so that advection is more important, then the oceanographic community made a huge advance and then this what is being used, and we have our own model for this. Well, having said that, I think I spent even more time than I was allowed. So thank you. Now,
any more questions?
master.
So you answered the question I was going to ask.
Yeah, about.
But could you, so what's the difference between the transfer of heat, which is not a material substance, and transport of a
Passive scalar.
material substance, like a passive scalar? So what's the reasoning behind one being larger, the effective diffusivity being larger than the other?
No, I didn't say it was large. I said salt was larger than heat. The salt is treated like temperature. Those are all active scalars. the big difference between active and passive scalar. Temperature and salinity are both active because they're both active.
But one is the substance and the other is a property.
Yeah, but they're both affecting the density.
Yeah, they're both
Sure,
affecting
sure.
the density. So in that sense,
That's the dynamics.
they're active. In the sense, the density enters in the velocity field, and therefore, whatever change the density affect the velocity. And so, if you have turbulence through doors, then they affect the velocity field, which then there's a feedback. A passive scalar is the one that is really an oil spill. If you have oil spill in the ocean, that is a passive scalar because it's being transported passive. They said it doesn't react back on the field. And one of the papers is precisely on what passive. So that if you ask me, the diffusivity of passive tracer is different than the diffusivity of either temperature or salt. And it's always in the middle. It's always larger than the smallest of those two, but never larger than the largest of the two. So if you have temperature and salinity, and if temperature is larger than salinity for some reason, then the concentration, which I discovered by doing that, I didn't think about it before, but the passive scalar, in my computation right, but the passive scalar is always larger than the small and smaller than the largest of the two active. That's as far as I can. I'm talking about vertical stuff.
So could your theory of associated with overshooting apply to things like overshooting of clouds into the stratosphere? Convective plumes that overshoot through the whole over the tropical.
Yeah, well, if there is no phase transition, perhaps yes. Because this is no phase. Even in the atmosphere, you have phase transition with the liquid and no.
That's the source of the.
That's right.
The energy.
That's the source of, that's the
But the
release.
overshooting itself is not related.
That,
No,
once you get the source of energy, then yes. Then the answer should be yes. It's a good point, yes. We never did it essentially for lack of manpower. But no, our model cannot handle phase transition. It shouldn't be to that. But if that you use phase transition only as a source of mixing, given that, then the procedure that we have developed should be able to handle those regions of overshoot. In other words, of mixing, by overshoot I mean mixing in region in which the mixing is not created locally. In other words, it's created there but it's transported, that's why it's not local. It's created there but it's transported here. So our models should be able to handle that. Successfully or not, that I cannot tell. But at least they have the ingredient of having this third order moment, which are exactly the one that represent no locality and third order moment at the same time, the same nomenclature. Because you transport stuff, you create stuff in the middle of the convective zone of the sun, just to give you an example, and that is being transported, and it's going to mix stuff that left on its own it would never mix because there's no local source. So in principle, the answer should be yes, provided, yeah, I think so.
But there's sort of a lot of uncertainty about what the relative balance of sources of tropospheric air getting into the stratosphere is. Is it primarily just sort of large scale ascent, or is there a significant source from the overshooting, convective overshooting into the stratosphere? Sort of an open question.
I imagine, no. I mean, imagine this, yeah, we should have a couple of more manpower just to use our model to that stuff, I wish we could. But we are underworked, underpaid, no, overworked, underpaid, understaffed, whatever it is. And yeah, but in principle, yeah, because unless you go into a regime in a regime in which you really have a dynamic of, because there is this whole contention whether this model can represent plumes, and plumes is a terminology that is commonly being used. In other words, and yes, since what we're doing is basically manipulating this Navier-Stokes equation, and Navier-Stokes equation, general equation, whether we call them plume or not, it doesn't make much difference. I tried to pluminize my equation once, and the referee said the worst term in English he ever heard, pluminize. I said, well, you give me another one and I'll do it, and he was not able to come up with anything. So I pluminized my equation, and because when you want to make them look, because there are plumes equations, people have in that. The G.I. Taylor who invented just about everything that was to be invented in his own time, invented the theory of plumes, where he was looking at plumes coming out of volcanoes, right? And he came up with, being smart man as he was, he came up with three equations, I think, phenomenological equations, which are still being used, and they will also be used in oceanography. I don't think they were ever used in your field, but they should, because they're the general. So my challenge was, are these equations have any resemblance to those plume equations? And so I pluminized my equation, which means that you do a lot of shampooing to it. And sure enough, because he was smart, the major term, the key term of his equation, they all come out. Perhaps all the other terms are irrelevant, and I'm carrying along a baggage of his relevant terms. It may well be. So in that sense, the plume equation has been very helpful for me to see what was very relevant and not very relevant. But after I did that, after this strong literary criticism when I used the word plume, I said, the hell with it. I will not do it anymore. But yes, I would like to do more work on that, but it's not that I don't want to do it, it's that there is a limited number of.
He needs a new postdoc.
Yeah, yeah, it's like a hole in my head. I did it. No, but I mean, those in the atmosphere, yeah. I mean, having this rich, quote unquote, treatment, etc., it's really bad that we cannot apply it more, honestly. I wish we, but now we're so busy with the ocean and the atmosphere that we cannot do it. But yeah, I know, but I know what you mean. I mean, it's, the only man who can do something is each chance, which will return to the atmosphere soon enough. Yeah.